Okay. All right, great. Going to just take a few minutes to recognize this year's theme for the Heliophysics Big Year, or this month's theme for the Heliophysics Big Year, which is environment and sustainability. So I'm just going to go through a few points to kind of think about the sun in a different way than we normally think about the sun, and just a reminder of how broad the influence of the sun is. So just going over a few things, the sun is important for supporting renewable energy and development. A lot of us are moving more towards solar energy as a clean and renewable source. This is obviously influenced by the sun's activity, so it's important to think of the sun in this context. We need to be able to make accurate predictions of solar radiation variations so that we can optimize solar power generation. Knowledge that we get of the sun can help us improve the efficiency of these types of technologies, improving global sustainability goals. Of course, the sun contributes to the Earth's environment because we are in the sun's environment. And so one of the things that's been very important as of late is to assess the role of the sun in global warming. A lot of people like to ascribe all of the recent global warming to the sun, but it's only by studying the sun's influence on global warming and its impact that we show that much of the warming that we've seen is actually more associated to the anthropogenic climate changes that we've seen. And so being able to assess the relative importance of anthropogenic warming versus how much is coming from the sun is important. Understanding this will also help us enhance our climate resilience and develop strategies to adjust to the changing climate. And then also will help us, prevent damage to our biosphere. Sudden bursts of radiation can impact our magnetosphere, leading to geomagnetic storms, which we've seen a lot of this year with the solar cycle maximum upon us. Increased UV radiation can cause damage to marine ecosystems, can impact coral reefs, photosynthesis, all of these things. And so monitoring the sun space weather, solar storms can help us find better ways to ensure sustainability for these natural habitats. The air travel is also impacted by space weather, especially since the planes aren't limited to the roads. They can have lots of variability on which paths they take. And often the most direct point between two airports is through a geodesic, which will very often take us over the poles, where you're much more susceptible to the radiation that comes through from space weather. And so, being able to better forecast solar events is important for us to be able to help protect, both the passengers and the crew on those types of flights. It's also important to agriculture. Changes in solar radiation can influence crop cycles, soil health, agricultural sustainability. Sustainable agriculture relies on understanding environmental factors like the solar cycle in order to help maintain food security across the globe. Also preserving global ecosystems. These things are also dependent on that. I think all of us are well aware of the importance of mitigating the effects of solar radiation on our Earth's technology. We know that this can influence our power grids, our satellites, our communication systems. All of our assets that are up in space are vulnerable to solar storms. And so being able to prepare for these disruptions and minimize the impact is very crucial, especially as we are embarking on the space age and moving more and more outside of the Earth's protective environment. And then also it's important for protecting the ozone layer, Earth's atmospheric effect. So the sun is important in lots of different ways, lots of different impacts on the the environment, and lots of different ways that we can use the things that we are learning as heliophysicists to help improve the sustainability for the future. So just some food for thought in honor of this month's theme. And I want to take a few minutes to just briefly mention that next month's Heliophysics Big Year theme is going to be solar cycle and solar cycle max. For all intensive purpose, this is our theme. This is what COFFIES is all about. And so we really want to take a concerted effort to be much more proactive and participating in the October theme. And COFFIES is starting to plan various different activities, and we really need your help with this. So just a highlight a few things that we've been thinking about, things that we're starting to put together, planetariums and exploratorium exhibits, particularly places that have a science on the sphere. Brian's going to be debuting a new magnetic sun science on the sphere exhibit this Saturday. I believe it's at the Berkeley Planetarium. So if you're in California, go check it out and say hi to Brian. But we'd also like to engage other science on the sphere locations. I'm going to be reaching out to the Fisk Planetarium here at CU and see if we can do a showing of the magnetic sun. And if there's a science on the sphere near you, let us know. Let's see if we can get this program set up on some of the planetariums, other planetariums across the U.S. We're going to be doing public lectures. Pay attention to see if there's any public lecture opportunities near you, particularly in the month of October, and let us know. We would like to advertise all of the activities that we'll be doing. And so if you've got a public lecture that you're going to be doing, or even if it's a professional seminar, let us know so we can share that with the community and the public at large. We're also considering doing an online panel where we'll have 3 to 4 presentations, 10-minute talks for the public, followed by an Ask Me Anything session where the public can engage us and ask questions. We're in talks with NASA to see if this is something that we can do as a live stream, but I don't have the word on that just yet. So that is a potential. And then we're also thinking about maybe recording and creating a public video that's more geared for kids. So some of the things that we're thinking about there. In terms of advertising, we're talking with Alex about getting all of this stuff put up on the website. We'll send out announcements via, for instance, Solar News, possibly engage with NASA, public outreach, social media to advertise some of these events. We really encourage everyone to do something. A few of you have already volunteered. You saw my email that went out yesterday, so thank you. We're definitely excited to have those volunteers, but we need more. So if there are more of you that are interested in participating in the October theme, please reach out to Lisa or Brian so that we can get you on our roster. And for those of you that are not so proactive, I'll be sending out more, Brian and I will be sending out more emails requesting help with some of these activities over the next month. Some of them might be on a very short fuse, so as soon as you can let us know what your availability is, please do. And if you have any other activities, COFFIES related activities, outreach activities, seminars, anything that you're doing that you've got already planned for October, please let us know so that we can include that as part of our program for the Heliophysics Big Year theme for October. So thank you very much. And I think we can pass it over to our primary speaker.
Okay, before Soumi present his seminar, let me introduce Soumi first. So Dr. Soumyaranjan Dash is currently a solar physics postdoctoral fellow at Institute for Astronomy, University of Hawaii at Mānoa, working with Professor Shudong Sun. He got his PhD from Indian Institute of Science Education and Research, Kolkata, in 2022, with his thesis focused on studying the solar magnetic field dynamics at different layers of the sun and deriving connections to its impact at a global scale on the heliosphere at different spatial temporal scales. Dr. Dash's current research interests include long-term solar coronal magnetic field evolution, surface magnetic field dynamics, polar field evolution, and solar wind simulations. Let's welcome Dr. Dash again, and I will pass over to Soumi for his seminar. We see your
Oh,
title page. Yep.
thank you. Thank you, Riju, for the nice introduction. I'd like to thank all the organizers for giving me this opportunity to present this work in front of this um, expert audience. So today I am trying to focus on our discussion with which revolves around magnetic flux transport on sun surface. Especially, I'll be talking about the application of Ensemble Kalman filter data assimilation technique, in which we will try to infer the surface flows using a flux transport model and Kalman filter assimilation techniques. So this is a work which is um evolving with multi-institute collaborations with Mark, Mosumi, Sudong, Sushant, Yang. I forgot to mention Todd also. And okay, so let's go there. Okay. Now, we know that magnetic fields are important. Sun's magnetic fields are important because they directly, the magnetic activity on the sun surface in the solar corona, they essentially shape the heliosphere and are near Earth space weather conditions. So it's important to understand how the magnetic field evolves on the sun. And since the magnetic field is generated by the MHD dynamo process on the surface, they get transported by all these advective flows with supergranular diffusion, and they shape the polar magnetic field, which roughly follows 11-year cycle period. Now, here you can see a butterfly diagram of the change in the surface magnetic field, the radial component of the magnetic field, how it changes over time. And you see that there is cyclic variation in the polar fields. The polar fields are particularly important to, since they directly can be used to estimate a following solar cycle strength. They are important from the perspective of understanding the distribution of the open flux in the global heliosphere, and not only surface magnetic fields in global scale are also important, since they are the essential drivers. I mean, they are the boundary conditions of coronal magnetic field models. That's why we need to understand how the magnetic field on sun surface changes, because we only have observations of one side of the sun. The far side of the sun is directly not observable, and also the observations that we have, they also suffer due to projection effects near the high latitude locations. That's why we primarily rely on surface flux transport models, which use a prescribed flow patterns and diffusion process. And that's how we can try and model the evolution of the surface magnetic field transport processes. Now, this is a plot of various Maiden flow profiles used by different groups. And as I said, the flux transport process on the sun is primarily driven by the horizontal plasma flow parameters and diffusion coefficient. Now here, various groups have used different kind of meridional flow profiles with different peak flow speeds for different hemispheres. Here is a set of those model parameters from different groups. I have not included, or I don't probably have access to all the observations and for the meridional flows, but there are also observational evidences of these meridional flows limited to certain latitudes, but there are also certain observational evidences of these flow profiles, not only on the surface, but also to some inner layers of the sun. Now, so here you can see there is some variation in the peak flow speed in both the hemispheres, and also there is a difference in the kind of profile different groups use to evolve the surface flux transport process, or evolve the magnetic fields on the solar surface. Now, this raises a question: since we are observing the magnetic fields and we're trying to model the magnetic fields, and this is a prescribed parameter, because different groups are using different parameters, this is to calibrate the final outputs, like the magnetic fields, to the observations. Like we have observational proxies of polar fields, And from the flux transport models, we can generate these polar fields, and then we can compare or calibrate our model accordingly. That's why we need, since there is a variation, we need to understand, since the observable is the same, but the prescription of this flow profile is different. We are trying to infer this flow profile or the parameters of the flow profile from the magnetic field observations using our Kalman filter technique. In this talk, I'll focus on our experiment with a one-dimensional flux transport model. Now, modeling surface magnetic field distribution is important since, as I discussed already, and we need to understand from observational how we can observationally constrain this flow profile and the parameters in addition to sunspot properties. And estimation of these parameters is not very easy. And we are trying here to use aseptic model and data assimilation techniques to infer this flow speed from direct magnetic field observations. So what is Ensemble Kalman filter technique? So this is a technique which is based on statistical multidimensional regression analysis, which uses a Bayesian approach with available observations. And this particular test bed is already developed at NCAR, and this has been applied to various other fields. For example, Earth's atmosphere models, space weather prediction models, and in two-dimensional backplate solar dynamo model as well. Now, what it does is we have for example, we have a physical model where one of the parameters, one of the input parameters is kind of unknown. And if we want to constrain this parameter based on the available observations, then we can utilize this Ensemble Kalman filter technique. So in this cartoon, what you can see is, for example, if this is the parameter which we are trying to constrain, and this is the actual value that we need to generate the actual observations. And these are the observations. For example, in the case of flux transport model, let's consider flux transport model and our peak flow speed of the middle flow. If this is the peak flow speed, and these are the initial guesses of the peak flow speed at time t0, and using all these initial guesses, we can generate the magnetic field using flux transport model. And since the initial guess of the peak flow speed is different, we expect to have differences in the output of the magnetic field. Now we know that, okay, this is the actual observation of the magnetic field. And if you use that to further constrain our initial guess, then in the next iteration, we probably would have our reconstruction of the state vector, which is the peak middle flow speed, which is closer to the actual value. And we can again use that in our aseptic model to generate an ensemble of magnetic fields, which are the observations. Now, this iterative process can go on for let's say number of n iterations, and at the end we will be left with a value of the true state, which is the peak flow speed, which is constrained by the magnetic field observations. So this is the overall uh, process that we will follow to utilize the Kalman filter technique. So now this initial guess is the prior ensemble state estimate, which are constructed from multivariate Gaussian distributions, and these are the posterior states, which are generated with tunable data assimilation parameters. The data assimilation parameters can be assimilation cadence, that can be errors associated with the observations. Those can be due to the number of ensembles. Those can be our starting point of the initial guess. And using those, all these parameters, we can, from the prior state, we can generate a ensemble mean of the model observations. And finally, we can try to minimize the covariance in the posterior state, so that we can finally reach towards a data constrained state vector, which provides us actual or true, close to true observations. Now here, the parameters for this particular experiment that needs to be constrained is the peak meridional flow speed, which is termed as state vector. Okay, let's understand mathematically how ensemble Kalman filter works. Okay, let's consider our flux transport model, where these magnetic fields are the observations at different times that evolve in response to the surface flows, diffusivity, and also we have included all the source terms, which are the BMR properties that shape or that evolve the surface radial magnetic field. Okay, so if we consider or if we construct an ensemble of states, that is the peak flow speeds, which have like this ensemble of state vectors will have varying peak flow speeds and model the flux transport process, then we can approach a true state. That is, those are the observations, which is the magnetic field values at different latitudes. For this experiment, we are only considering one particular latitude, which is at 60° north latitude. We can in principle consider multiple latitude locations and different and we can also make our flow profile time dependent, and we can do that, but that will increase the dimensionality of the problem since it involves ensemble evolution of the whole state and observations. It will increase the dimensionality, and hence the computation will be probably a little bit computationally more demanding. So that's why for this particular experiment, we are only considering one particular latitude point to sample our magnetic fields. Those are the observations, and one particular parameter, which is the peak flow speed only. Now, okay, if this xt is our state vector, which we can generate using this M operator, which is basically a random walk operator that generates ensemble of states at a particular time, and that can be modified based on the prior estimates of the state vector. Now, our forward operator, which is y0, so y0 is our observation that is generated using the forward operator, which is our surface flux transport model, which is H, and E0 is our epsilon 0 is our error associated with this observations or this forward operator. Since we are using a numerical PD solver, it's basically exact within the bounds of the numerical scheme that we have used. That's why we probably would not have ensemble 0 at this particular stage, but from the actual observations, there is possibility of observational error associated with the observations of the magnetic fields. Now, what we need to do is this error in the observations. Okay, so this error in the observations can come from the uncertainty in the initial condition. For example, that can come from the meridional flow speed, amplitude, or the profile, or the synoptic observations of the magnetic field itself. And it can come from the diffusivity as well. And this error can also originate from the model limitations as well. I mean, for example, we probably the simplified version of the surface flux transport model, which solves basically the radial component of the magnetic induction equation, probably does not include all the physics that we are observing from the sun into the model. So this error can originate from these two sources. But in this ensemble Kalman filter technique, we are only focusing on the type 1 kind of errors associated with the observations. Now, for the prior estimates of the state vector, the error can be estimated like epsilon p, which is basically if xtr is the true state or the actual value of the peak flow speed, then this the error in the prior estimate of the states can be written like this. And similarly for the analysis states, which are basically the posterior states, this is the error associated with it. Okay, so now this is the error error covariance in the observations, and this is the error covariance in the prior estimates. Now we need to calculate what is the error covariance associated with the analysis state, which is with the posterior estimates. Now this can be modeled with this simple probability computation. So according to Weis theorem, what we can do is we can write something like this, and then the two terms in the numerator can be easily decomposed by assuming that the state vector is drawn from a Gaussian multivariate Gaussian distribution. The numerator can be described like this, and the exponents of, I mean, if you replace these expressions into the probability expression, then we can minimize the exponent, something like this, which is basically the expression, the mathematical expression for the Kalman filter assimilation technique. So this is basically our posterior state vector estimates that can be further used to drive the observations forward. So in this ensemble method, ensemble of state vectors are constructed from a multivariate Gaussian distribution. The posterior states are generated from the prior state vector, so that the above relation, so this basic relation holds for the ensemble mean and covariance. This is known as ensemble Kalman filter technique. Okay, so this is overall mathematical description. Let's understand how our flux transport model works. So this is a reduced version of the actual two-dimensional flux transport model. Since mostly our advective components like the Mendel flow and the differential rotation, they mostly rely on latitude we model these flows as a function of latitude. So we can see, I mean, this is shown by various literatures that the actual dipole moment only depends on the meridional component of or the latitudinal component of the magnetic field. So we can easily reduce our two-dimensional flux transport model into a one-dimensional model by averaging the magnetic field in the longitude. So this is the expression of our reduced flux transport model, where D is the diffusivity and S is the S is assigned latitude. And now this Vs is our meridional flow speed. So now if this is our meridional flow speed profile, which is inspired by this particular paper, where du is representative of the peak flow speed, and we are essentially trying to constrain this peak flow speed from our observations of or from our observations of the magnetic field. So this is output of our one-dimensional model, which is ran for about 14 years with a diffusivity value of 450 kilometers squares per second. And this above panel shows a butterfly diagram of the radial component of the magnetic field over this time frame. And this lower panel shows analogous butterfly diagram constructed from available HMI Carrington rotation maps. And you see, I mean, there are also some deviations in this peak flow speed, but overall, this butterfly diagram is qualitatively good enough for our experiment. And this is the distribution of the dipoles or the source terms as taken from the HMI 720s CA sharp CA 722nd database. And this is our so this blue curve shows the actual dipole moment calculated from HMI synoptic maps, and this orange curve shows the actual dipole moment calculated from our SFT generated butterfly diagram. And this is the meridional flow profile that we have used to generate to evolve this 14-year long flux transport process. And here you see this peak flow speed is set to be 30.7 meter per second, which is relatively a little bit higher. But for this experiment, we will consider this 30.7 as our true state, and then we will try to reconstruct our this particular this particular peak flow speed with ensemble Kalman filter technique by using magnetic field values at this particular latitude location, which is 60 degree north. Now, for running a successful data assimilation process, we need our model, or this time-dependent model needs to have proper restart functionality. In order to show that our model actually does have that, we have stopped the flux transport or the evolution of the acceptive model at different timestamps, and then compared and then used these as initial conditions to drive the model forward, and then stopped again, and then saw that, okay, the various time steps do match, and this basically validates that our restart functionality works. Because since the ensemble Kalman filter technique needs to have different assimilation cadence, and at each assimilation cadence, the global run needs to stop, and then the posterior state will be estimated using those observations of the magnetic field at a particular latitude, and then start from that point onwards till the next assimilation step to generate the next set of estimates of the posterior state variables. Okay, so let's go to some of the results from this experiment. Okay, so as I said, our observations is sampled at only one particular latitude value for this experiment, and that is at 60 degree north latitude. And this is the evolution of the magnetic field at that particular latitude location. And this is the reconstructed observations. This is just to show that, okay, this is our baseline, and we will try and compare first by changing the assimilation cadence. I mean, how the reconstruction of the state vectors, which is the peak flow speed, is impacted by changing by using different assimilation cadence values. Okay, so this plot shows here is the panel A shows the reconstructed magnetic field values at 60 degree north location for different assimilation cadence values. By different assimilation cadence, I mean that after each 1 day, for example, if we consider this cadence of 1 day, so this means that at each 1 day, the simulation is stopped, and the state vectors are again, the posterior state vectors are reconstructed using observations or the magnetic field values, and I mean, they are further constrained or corrected to generate the next set of observations. So similarly, this different values of the assimilation cadence varies like this. Since I mean, for this numerical experiment, we can set the dt of the simulation, which is like the minimum time step of the simulation by hand. I mean, we do have control over that, but from actual observations, we probably will only have the global observation of the magnetic field as one Carrington rotation map, which spans, I mean, which we only have access to after each 27 to 28 days. So in that case, the assimilation cadence, like correcting the state vector or constraining the state vector, can only happen after that particular timestamp, which is roughly 30 days. I mean, we can consider 30 days from our experiment as an example, which is close to those kind of assimilation process. Now here you see that there is a lot of variation in the reconstruction of the flow speed for different assimilation cadence values. And initially for all the assimilation cadence values, there is initial variation around the true state, which is 30.7. But later for some of the for some of the experimental cases, for example, like here you can see that 10, 20, 30, 60, and even till 150, the reconstruction holds relatively well. The constructed value of the peak flow speed actually does give us close to our true value of the peak flow speed. The deviation happens when we try to assimilate too often. For example, this for the case of 1 day, this is known as ensemble collapse, which I'll describe after a little while. And for the case of 180 days and for example, for 200 days, the reconstruction of the peak flow speed is relatively very bad. Now, this is kind of expected because the coupling between the peak flow speed and that impacts the evolution of the surface magnetic field is after 180 days, this coupling is kind of lost. So we need to choose for any particular system, for any particular physical system where we know that how the parameter, how the state vector impacts how impacts the generation of the observations. We need to constrain our assimilation cadence, or we need to limit our assimilation cadence to a certain value which can cover and that which can cover that particular coupling. Okay. Now, if we, as I said, for a experimental case of assimilation cadence of around 30 days, as you can see that this reconstruction of the peak flow speed is relatively well maintained. That here you see that this dark curve is the ensemble state mean, and these are all the light pink are all the ensemble states of the peak flow speed, and this is here you can see this is the actual the true state of the peak flow speed, and you see that close to and after a certain while the reconstructed peak flow speed by data assimilation process is approaching the true state value. So this says that we can perform this experiment with various assimilation cadence, and we will end up with having a value of the true peak flow speed after a certain value. Okay, now if we consider the assimilation cadence of 1 day, which is too often, and by too often I mean that within 1 day of assimilation, and after that day of assimilation, if we try to change our state vector, which is the peak flow speed, and then try and generate our observations, then it will basically not have enough time to relax, or the flux will not have enough time to react to the dispersal due to the Medinal flow speed, due to the Medinal flow profile, which will result in collapse of reconstruction in the peak flow speed that you can see here. And the final reconstructed peak flow speed is way away from the true peak flow speed of 30.7 meter per second. This is known as ensemble collapse. Since since we are using SFT model, our model evolution has a time step of roughly 4 hours, and we are trying to assimilate our data as quickly as one day, which is not suitable, and that results in this ensemble collapse process. Now, another tunable parameter in data assimilation process is our error associated with the observations. Since we are using a numerical model here, which is which is kind of exact, but within the bounds of the numerical scheme that we are using, and that's why we have here, for this experimental purposes, we have artificially increased the error associated with the numerically generated magnetic fields at these location, at this 60° north location, and then try and reconstruct the state vector, which is the peak flow speed of the Medinal flow, And as you see that if the error associated with the observations is too high, then the reconstruction is relatively bad. And by bad, I mean this the actual value is 30.7, but we at the end we are for a value for an error of 10 power minus 2, we can only reconstruct up to an accuracy of 29.9, which is roughly 1 meter per second away from the true peak flow speed value. And again, here in this case also, you can see that initially there is a oscillation around the true peak flow speed value, which is denoted by this black curve. And later, as we evolve with time, this ensemble of states approaches the actual or the true state value of the peak flow speed. Now, we can also experiment with the number of ensembles. Since this is an ensemble-based modeling technique, we can also try to increase the accuracy of our reconstruction by changing the ensemble size. Here we have experimented with various ensemble size, starting from a size of 2 to ensemble size of 70. And what we observed is with increased ensemble size, the quality of the reconstruction of the state vector, which is the peak flow speed, is not does not affect is not affected drastically, but it closely approaches towards the true state. And we are already at a point for ensemble size of 20 to 25, which is close to the reconstructed peak flow speed, which is close to the true state value. And in this case also, initially there is oscillation around the true state of a true state, but later again it approaches towards the true state as the reconstructed peak flow speeds approach the true state as we try and assimilate with different ensemble sizes here. So what it says is the peak flow speed can be successfully reconstructed with this assimilation technique. And this overall algorithm is very versatile. This can be used in any other physical systems to constrain the free parameters which are otherwise unknown. And for this particular experiment, we have tried to experiment on different tunable parameters of the data assimilation process, which are like assimilation frequency, the error associated with the observations, the initial guess of the state vector, and then ensemble size. And we have seen the changes in the reconstruction of the state vector. And we are fairly certain that if we use since this was an experiment with artificial data generated using surface flux transport generated magnetic fields, we can in principle use the actual observations of the magnetic fields to constrain the meridional flow speed and the profile. Probably we can constrain the hemispheric asymmetry in the flow speed across different hemispheres. We can probably reconstruct the solar cycle dependence of the flow speeds and the local flow perturbations if we use a higher dimensional version of this algorithm. And we are working towards that right now. And we have submitted this particular draft to APTIO, which is under review right now. And we will see how we can evolve further with our technique. So thank you. That's all I have. Thank you so much for listening. If there are any questions, I'd be happy to answer.
Thank you, Soumi. I was just trying to unmute myself. So we have some time to take questions. I sorry if I interrupt someone. I heard someone was about to speak something.
Well, I have a question. My name's Ewing. Question: how did you choose the latitudinal profile of the flow.
Okay. Okay, so this is the middle flow profile that we have used here for this model.
Oh, it's just it's not based on your measurements. You just took it from someone.
This is analytical expression. Yes, this is not directly from observations, right?
Does it even make sense to, I mean, if you're using a flow profile that's completely unrealistic, does it even make sense to do these sort of simulations?
So okay, so if we use this middle flow profile, we can, okay, so we are generating this 14-year long evolution of the surface radial component of the magnetic field. And if we calculate the actual dipole moment from our simulation and compare it to the observations, like actual dipole moment calculated from the HMI synoptic maps, then we see a good match with our simulation and the observations. That's why we have restricted
Well,
for this experiment.
I
But
don't think that's
understand-
enough. I mean,
I do
they're probably, I mean, there's probably 100 different profiles that would give you a good match.
Yes, yes. So as I initially said that, okay, so various groups have used multiple different Merton flow profiles for their experiments, for their flux transport models. And also there are observational evidence of observational reconstruction of the Merton flow profile uh, by different techniques, by different groups. But we are approaching or we are developing our model towards inferring this flow profiles directly from magnetic field observations only, by not assuming anything prior to our initial guesses. I mean, we will try to use the magnetic fields to generate these kind of flow profiles. Or even if we assume an initial guess, then towards the end of our assimilation process, we will be left with a flow profile which is constrained by the magnetic field observations.
It would be interesting if so that you show a bunch of different profiles. So if you used each one and then, compare what you get, that might be useful.
Right. Okay, thank you for the suggestion. We will try to look into that. But since this is again a numerical experiment, so the true state that we provide, that we prescribe as our initial true state, our model will try to converge towards that at the end. So we'll be left with the initial true state that we provided. So that's why this is probably not so, since again these different profiles are they come with different set of numerical schemes that are used in the respective flux transport model, and the kind of prescription of the source terms, so that they are calibrated to the observations accordingly. So definitely we'll look into this particular point.
Yeah, and they are also probably, well, some are just pure measurements. Some are based on simulations, and the simulations depend on things like your diffusion coefficient.
Yes,
Like you
yes.
use 450, but if you use a different value, you'll probably find you need a different flow profile.
Yes. That's true. Yes.
Okay, any other questions? You can either raise a hand or just speak up. Okay, it seems there are no other questions.
May I
Oh,
make a
Masumi?
comment?
Oh,
Yes.
please ask.
I was thinking of making a comment to Yiming's question. Yiming, Shomo has focused on only one parameter at the moment, that is flow speed. So the question you are asking about the latitudinal profile, so he needs to include more parameters, so multiple parameter reconstruction at at the same time. And that is definitely one of the future projects he will be looking at. And in that case, it will any kind of gas will be fine. And then utilizing the observation, magnetic field observation, polar field observations, he can reconstruct the spatial profile also.
Yeah, one thing, I think the profile he's using now, it looks a lot like the one that Hathaway and Upton Hathaway used. And as you pointed out, the way they derive that profile, it doesn't make much sense because they just track magnetic features. And as you pointed out a long time ago, if you track magnetic features, you're including the effect of the supergranular flows, the diffusive rates. And if
Actually, that's
you-
not true, Yuming. We've actually shown, we have a paper where we've shown
Yeah,
that it
I
actually
know,
does not
but-
include the effects of the diffusion.
Well, yeah, I've seen the paper, but I don't believe it. I mean, the diffusion definitely is affecting the effect of the diffusion is you have the flux concentrations in the active region zones. So you have diffusion polewards and equatorwards from the active regions. So that diffusion, if you include that effect in your measurements, magnetic tracking, which I think you have to, then, I mean, if you're just tracking magnetic features, then you're going to find that the flow profile, the velocity peaks at much higher latitudes than it actually does, because that poleward flow is being boosted by the diffusion from the active regions. And Masumi pointed that out, and I pointed that out, but no one listens.
Well, that's because we've actually done the simulations and we've measured an input flow from our simulations, which include a diffusion, and we are able to recover the meridian flow that we actually put in. So I think we've shown that the method is robust and is not impacted by that diffusivity. But I think that's an argument that's probably better had at a different
Do you
forum.
have a physical explanation why the diffusivity doesn't impact the magnetic tracking?
Yeah, because
I just
we're not tracking individual magnetic elements. We're tracking the bulk motion of the magnetic network pattern. We're doing a pattern tracking method, not a individual feature tracking method. But again, I'm
I
not sure that
think,
this is the right forum for that discussion. I'd be happy to chat with you about it more.
And I think SOMO has used a flow pattern that is peaked at 25 degree.
Yeah,
So
and it's much stronger than
Yeah.
in any of the observed flow measurements.
yeah. So I
Yeah.
think that is consistent with Doppler and ring diagram and everything. Isn't that true? I think it's
Yeah.
kind of an average of all measurements.
Although it is much stronger, it's 30 meters per second, which I think is stronger than most of the observations.
Yes, speed is stronger.
Yeah.
I think I think Yiming is talking about profile.
Oh, like
This flow
structure, yeah.
peaks more closer to 20 degree, I think like 25 degree or so,
Mhm.
which is a kind of average of all measurements, something like that.
So for the stronger speed, we have used a little increased value of magnetic diffusivity. If 450 kilometers square per second on the surface is a little bit high, so that probably compensates for this.
It depends on who you ask.
Right.
Yeah. And it also depends on the scale,
Yes,
it's scale
yeah.
dependent.
Anyway, I think the main point is that it's a very powerful technique, and from the observation of magnetic field evolution, it can be reconstructed and can be compared. So
Yeah, I'm looking forward to seeing what you get when you apply it to the observations. It's very exciting. Another technique to share.
Okay, we are at our 1 hour time now. If no more questions, we can thank our speaker today, and thank you for everyone for attending our seminar. So next month we will have more COFFIES events in regarding to the Heliophysics Big Year theme that is for solar cycle. So looking forward to see many of you in next month's events by COFFIES. See you then. Bye.
Thank you. Thank you, everyone. Bye-bye.
Thank you, Soumi.
But